All righty, here we are, lads and ladies. Good morning. Welcome back to Calc 2. Today is going to be a fun day for us. So today we are going to talk about volumes. It's our first kind of foray into these new geometry problems. Last week we talked a bit about areas between curves. This you can think of as kind of an extension of that work. The procedures for solving the problems will be somewhat similar in that you're going to be given some curves. You'll have to sketch the region bounded by those curves. But then instead of calculating the area of that region, you're going to imagine rotating that region and finding the volume of the solid which is generated when you do that. There will be, of course, a new homework set associated with this. Your first homework was due today at the start of class. If you need more time on that first homework set, you can submit an extension request within WebAssign. All right, let's get the dot cam talking to the computer. Throw up the title card and we'll get moving. Okay, here we go. So this is MAC 2312, section number 004, which is of course Calc 2. And today is the 10th of January 2022. Today, about volumes. And we're actually going to talk about volumes not just today, but also on Wednesday. There's another kind of set of methods. Today we're going to talk about the slicing, which is AKA the disk washer method. Okay. So the basic idea is this. We're going to find first a little volume, a tiny, tiny portion of the volume of that whole solid we're trying to find the volume of. And then we're going to integrate that little volume. We're going to add up all the little volumes to get the total volume of our solid. That's kind of the way you should think about this. Here, those little volumes, you can think of as little cross-sectional slices of the whole thing. So sort of the picture that you'll find in the book, you have some, maybe complicated 3D shape, something like this. And what we're going to do is we're going to think of there as being an axis running through this thing. Call it maybe the x-axis. And we will take a little slice of this object. Take just a little slice of it. And then you will, you're thinking of this whole object as being a bunch of little slices like these stacked up on top of each other. So if I say this slice is at position X and the area of the cross section is A of X, and the thickness of this little slice is dx, then we can say the following things. The volume of that slice which I will call dV, is the area of this cross section times the thickness of the cross section. So that's A of X times dx. And then if I can say that this whole object starts over here at x equals a and ends over here at x equals b, then this would tell us that the volume of the solid altogether would be the integral from a to b of dv, which is the integral from a to b of a of x dx. So this is kind of the overview, right? This is how you should think of these things in general. You've got some three-dimensional solid. You're going to find a formula for the volume of a little differential thickness slice of that solid, hence the name, slicing. Once you find that little volume, which is the thing we call dV, and in this case, we'll calculate it as the cross-sectional area times the thickness. Once you find the formula for dV, you will use the integral to add up all of those little volumes, giving you the full volume. Now, in practice, most of the solids we're going to look at are going to come from rotating a region about an axis. So they will be more symmetric than this guy. They'll have some rotational symmetry. But this could, in theory, work for asymmetric solids as well, like the one we've drawn there. Your textbook has a nicer picture of this, which I might as well show you. Here it is. All right, so here you can think of this big three-dimensional solid as being made up of a bunch of very thin slices like these. If you can find a formula for the area of that cross-section, then you multiply by dx and integrate, right? Here they're showing it with delta x's, and you're thinking of these as being little Riemann sum things. But that's the end result. So how do we do this? Well, let me start with a nice simple example. Let's take a cone. And let's orient it in the XY plane. Like so. I'll say that this cone has a height. Normally we think of the height as being like this dimension, right? Call that the height, h. And it has a radius, which I'll call, I don't want to call it r because we're going to use r for something else. So I'll just call this r naught, r sub 0. So this is a normal cone, right? Just as you think of the word cone. Its height is h, its radius is r naught. I've tipped it on its side and had the x-axis poking through it. If I want to apply this logic to finding this volume, then what I need to do is take a little slice of this cone. So let me do that here. And you see that that slice is shaped like a little disc. That's the origin of the other name for this method, right? The disc washer method. I think of this disc as having a thickness dx, just a tiny little differential thickness. And I think of it as being along the x-axis at an arbitrary position, which I will label as x. So then the other thing I need is the cross-sectional area, right? I need to know the area of this slice. So the area of the cross-section, it's the thing that we call A of X up there. This cross-section is a circle, right? So that's pi times the radius squared, where r is the radius of the circular cross-section. And the question is, can you find a formula for that radius as a function of where I'm taking the cross-section, where I'm taking the slice? If I were to take the slice over here, then that radius is very small. If I were to take the slice like way down here, then that radius is very large. Can I find a formula for the radius that will give me the radius if my slice was back here, and if my slice was up here, a radius that works everywhere along here? All right, a formula for that radius that works everywhere along there. The trick is to use similar triangles. So if I redraw this picture, just looking two-dimensionally, maybe I'll just draw the quadrant 1 part, right? Just drawing this part in 2 dimensions. This is R0, the radius of my base. This is H, the height of my cone. And my slice is right here at an arbitrary position X between 0 and H. Does anybody remember what similar triangles are? What does it mean to say two triangles are similar, and what can we deduce? Anybody? Okay, two triangles are called similar if they have all the same angles inside them, which is equivalent to saying their ratios of side lengths are the same. Right? That's what it means to say two triangles are similar. So if you look at the big triangle here and the little triangle here, they're both right triangles. They both have one 90-degree angle, and they share this angle back here. So they must have all three being the same angles, right? Whatever this angle is, this 90-degree angle, those are both shared, which means this angle and this angle have to be the same. These triangles, the big right triangle here and the little right triangle here, are similar, which means their ratios of side lengths are the same. The thing I'm looking for is this radius, right? I want to find the radius of this cross section as a function of X, where I'm taking the cross section, right? I can draw the radius in here. It's this distance. And by similar triangles, this big triangle being similar to this little triangle, the ratio of side lengths R0 over H has to be the same as the ratio of side lengths R over X. R over X is equal to R0 over H. Multiplying both sides here by X, we get that R is equal to R0 over H times X. So this is what we were looking for. We were looking for the radius of my disk here, the radius of this slice, as a function of X. If X is very small over here, that radius is very small. And you see if you plug a small number in for X here, this will be quite small. If X is equal to H over here, then this radius is equal to R0, which is the radius of the base of this cone, which is what we want. Therefore, the area of that cross section as a function of where I take the cross section, X, is equal to pi times the radius squared, and the radius is R0 over H times X. So we have that squared. All right, and we're almost ready to set up our integral here. So I want to take a second and pause. Any questions about the similar triangle argument or what this radius is and why we need it? Anything like that? Okay, simplifying a little bit here, pi times R0 over H times X all squared is pi R0 squared over H squared times X squared. And now I'm ready to write down my integral. The integral for the volume is the integral from A to B of the little differential volume. That little differential volume is A of X times dx, where A of X is the cross-sectional area, the thing we just found. So if I'm going to set up the integral for the volume of this cone, that's going to be the integral of A of X dx taken from the smallest X value in this region, which over here is 0, to the largest X value in this region right here, which is H, right? Because the height of the cone is H. So that's the integral from X equals 0 to X equals H of my cross-sectional area times dx. Oh, I do see there's something in the chat there. Rather than trying to cycle back through the whole problem, could you ask, be maybe a little more specific about which part we want to see again? Sure, the similar triangle part. Okay, so two triangles are called similar if the ratio of their side lengths are the same, which is equivalent to saying they have the same angles. What I want is this radius right here, right? This is the 2D projection of this picture. I'm looking just at this part and I'm looking at it in 2D. So I get a little right triangle here. My slice that I've taken creates another little right triangle embedded within the first. Because this little right triangle, which I've drawn over here, is embedded within the first one, All right, the word is inscribed. They are similar triangles, which means the ratio of side lengths are the same. In other words, when you take one side length and divide it by the other for the big triangle, that's the same as when you take one side length and divide it by the other for the little. That's what similar triangles mean. So if I take the radius divided by, if I take this opposite side divided by this adjacent side for the big triangle, that's the same as this opposite divided by the adjacent for the little triangle. For the big triangle, the opposite side is R naught and the adjacent side is H. So R naught over H must be equal to the same ratio for the smaller triangle, this opposite over this adjacent. Well, this opposite is little r, the radius that I'm looking for, and this adjacent side length here is x, right? That's the distance along the x-axis from the origin to where I took my slice. So r naught over h must be equal to r over x, which I've written here. R over x equals r naught over h. That's the similar triangle argument. Okay, from here things are not bad. I'm integrating from 0 to h this function a of x, which is pi times r naught squared over h squared times x squared dx. The pi, the r naught, and the h are all constants, right? Pi is definitely just a constant. R naught is the radius of the base of my cone. H is the height of my cone. The only thing that's a variable here is the x squared. So I can pop out pi r naught squared over h squared. And what's left is just the integral from 0 to h of x squared dx. I'm sorry if you hear the crying in the background. My son got very sick over the weekend. We had to take him to the hospital. He's got a high fever. It's been terrible. Okay, so we set up our integral by finding the cross-sectional area. We used a similar triangles trick to do that. Now we just need to evaluate this integral, and the first step there is to pop out all the constants. These are all constants. They all pop out. Now I just need to integrate x squared from 0 to h. An antiderivative for x squared is 1/3 x cubed. That's coming from my power rule. And I don't use a plus c here. It's a definite integral. I do evaluate between bounds. And what we're going to see when we plug in is a formula that may be familiar to you from geometry. This is pi r naught squared over h squared times 1/3 h cubed minus 1/3 times 0 cubed. And this whole portion here is 0 because 0 cubed is 0. 1/3 times 0 is 0. So I will have altogether here pi r naught squared over h squared times 1/3 h cubed. I have an h squared downstairs and an h cubed upstairs. Those cancel to just h upstairs. And the end result is the formula you may remember from high school, 1/3 pi times the radius of your cone squared times the height. That's it. That is the volume of a right circular cone. Okay. So I'm going to work backwards through this now, checking for questions. We'll start with the integration work. Are there any questions about the steps visible right now? Okay. Any questions about the similar triangle work on the right here? Does everybody see the little triangle and the big triangle it is similar to? The little triangle is right here in blue, and the big triangle is out here in purple. Those two triangles share the same angles. Therefore, the trig functions on this angle in here would be the same, which means that the ratio of side lengths are the same. Specifically, the tangent is the same. Since this is the same angle in here for the little triangle and the big triangle, the tangent of that angle, which is the opposite over the adjacent, must be the same. So this opposite over this adjacent, which is r over x, is the same as this opposite over this adjacent, which is r naught over h. I wanted that radius as a function of x. That's what I needed in order to set up my integral. So I take this relation from the similar triangles and I solve it for r by multiplying both sides by x. That's where I got this. Once I had this, I can plug it into the formula for the area of a circle. The cross section of this is a circle. So plugging this in to this formula for the radius, I got a of x is pi times that expression squared, because this is r, my radius. And then we just slap on a dx and integrate. Really not too bad. All right, this is an example where we approached the problem from the perspective of slicing. Most of the problems you will not approach that way, although you are always free to do so. I acknowledge that the geometry there can be a little bit intimidating, especially if you're not used to making arguments like this. And that's why there's a slightly more formulaic approach that works for pretty much every problem you're going to encounter. It just requires one thing, and that's that we talk about solids of revolution. So a solid of revolution, this is just a name for a three-dimensional solid that is generated by rotating a two-dimensional space. So these are 3D solids which come from rotating two-D regions about some line, generally called the axis of rotation. I'm going to show you some very simple examples of solids of revolution, and then I'll show you how we can simplify the volume problems by thinking about our objects as solids of revolution. So let's start with something uber simple. Here I have the horizontal line y equals 2. Here's my x-axis. Here's my y-axis. And if I look at this guy from x equals 1, say, to x equals 3, that cordons off a little region. Okay, so this is kind of like a 6.1 thing, right? I'm defining the area bounded by a curve. There's the region. It's the region from x equals 1 to x equals 3 that's bounded by the very boring curve y equals 2, the constant function y equals 2. If I take this region and I rotate it around the x-axis, I want everybody to just stop for a minute and imagine what's going to happen. Imagine that the x-axis is like a barbecue spit, and I can spin this whole picture around that. This little rectangle is going to pop out of the page, come at you, and then go back into the page and spin around. If you take a rectangular object and you spin it around, that sweeps out a certain shape. What is the name of the shape that will be swept out, the 3D shape that will be swept out as this rectangle spins around this axis? You all know this word. What is it? Very good. Yeah, Amanda and Tyler, it's a cylinder, right? It's going to give us a cylinder. In fact, I'll draw it over here. Let me continue my axis of rotation here. Here's the cylinder. All right, so as that region rotates, it will sweep out a cylinder like this. That's the idea. All right, this is a solid of revolution. It is the solid that is obtained by rotating this region about the x-axis. That's what we mean by solid of revolution. This generates a cylinder. The solid from the previous problem can also be thought of as a solid of revolution. If you take this line, which is y equals r naught over h times x, and you look at it from 0 to h, then rotate this around the x-axis. Again, think about this guy rotating. This will give you the exact cone that we were working with in the previous problem. Right? So that cone we were fiddling with in the previous problem can also be thought of as a solid of rotation. Here we're rotating a linear function about the x-axis. These solids can get considerably more complicated, right? And that's where we're going to go with this. They can have curvy boundaries. They can be quite interesting in shape. But we need to get comfortable passing from the 2D picture, rotating to get the 3D picture. It turns out pretty much all the work we're going to do to find the volume is going to be done in the 2D picture. You're going to come over here and do some distance finding and then integrate that to get the solid's volume here. But we need to be comfortable visualizing this rotation process. All right, so these are what solids of rotation are. Let me do one more. All right, if I take the upper semicircle, which here y is, we'll say 1 minus x squared. So this point right here, this would be 1, 0. This point up here would be 0, 1. If I take this guy and I rotate it around the x-axis, what's the name for the solid that would be produced by that? Yeah, good. This would be a sphere, right? And again, I can imagine my axis of rotation over here. And I'll do my best to draw you a nice sphere. All right, we would get a sphere like this. And here's that. There it is, right? We would get a sphere. Okay. So this is how solids can be thought of as coming from rotated 2D regions. And it turns out that thinking about those 2D regions as being the origin of your 3D solid makes the volume finding procedure a lot simpler. I'm going to show you another example now, and then I'll kind of describe the method in general. Rather than just like showing you the method in general, which can be a little scary, we'll do it through an example. First, are there any questions about where any of these 3D solids came from? How we're getting them as these rotated things? Okay. So what I'd like to do next is I'm going to give you a slightly more complex looking 2D region. And we're going to find the volume of the solid generated by rotating the region bounded by y equals e to the x and the x-axis from x equals 0 to x equals 1. These problems tend to be a little bit wordy, so in the future I'll just say, find the volume, and then I'll list the boundary curves and any other information you need. Now we need one more thing here about the x-axis. Sorry, my son's fever is coming back. Lots of trouble. Grandma is here to help us. Okay. So the first thing you need to do to solve a problem like this, and I'm going to give you the steps here. The first step, draw the curve. You need to practice drawing these graphs, whatever graphs you have in your problem, by hand. Do not just click through in WebAssign until you get it right. If you don't practice this, you will bomb it on the test. I promise you there will be problems on the test that require you to do this. all the basics you need. If you forget one of these, remember, is in the modules. If you come to the modules here in Canvas, go down to the bottom, graphs of parent functions, you need to know these. I'm not kidding. Right? Here are all those basic graphs you need to know. If you want to look at one of them, just mute all the others, right? So we need the graph of e to the x. That's the only one we need here. This is what e to the x looks like. Has a horizontal asymptote over here on the left. It's an increasing function. This is the curve y equals e to the x. Say this is 1. Here's my region, right? We're looking from x equals 0 to x equals 1. So this is that region that we are rotating. Step 1, draw your graph. Step 2, shade your region, right? Identify and shade your region. It's not always immediately obvious what your region is, even if you've drawn your graph correctly. So sometimes you'll need to think about that a little carefully. Step 1, draw the graph. Step 2, identify and shade the region. Step 3, add in your axis of rotation. Here, we're just rotating around the x-axis. Later, we will rotate about other lines. But for now, that's it. Okay. If you want to draw the whole 3D solid, you can do that too. I will do my best here. I will not do this in the future. I'm going to extend my axis of rotation over here. The whole 3D solid looks, in this case, something like this. All right, I know my art is bad. Yes, I feel bad. All right, something like that. That's your 3D solid here. This is obviously not meant to be a straight line. It should be curvy, symmetric to the top. All right, that's the solid you're going to get. We want to find the volume of this bad boy. The way we do that, we could go through that whole procedure of like thinking about a slice of this thing and finding a formula for the cross-sectional area, but I've got a much cleaner procedure for you. It just requires that you draw in a little strip here. The strip I will always draw. So the only thing here that is optional is drawing the whole 3D solid. This part and nothing else is optional. Everything else is necessary. It will always be understood that this strip is at an arbitrary x value within your region, right? An arbitrary position within your region, and the strip is always perpendicular to the axis of rotation. Now imagine rotating just the strip. If I take something like this and I rotate it, that will create a disk. So if I were to rotate just the strip, not the whole region, just the strip, that will create a little, very thin disk, hence the name disk washer method. All right, I'll show you the washers later. Here's the disk we get from rotating just that little strip. It has a very thin thickness to it. That thin thickness we call dx. It also has a radius, which I will call r. The volume of this little strip can be calculated as the cross-sectional area times the thickness. The area of a circle is pi times the radius squared, and the thickness of this little disk is dx. So that is the volume of this little disk. The big idea in this section is that you can think of the big solid here as being a bunch of these little disks all stacked up. And the way you calculate the volume of the big solid is by finding a formula for the little volume dV and then integrating that, because the integral adds those up. That's what an integral does. It's a continuous sum. So what I need to do is find the formula for dV as a function of x, just like we did before, right? Just like we did with the cone. And as with the cone, the trick is finding this radius. My suggestion to you is to come back to your picture and label things here. So this distance, the distance from the far end of the strip to the axis of rotation, is your radius. I need to pause for just a second, guys. I'm sorry. All right, sorry, kids getting more sick. I'm trying to make a plan for the rest of the day. Okay, so need to find the volume of this little disk. The volume of this little disk we call dV, and it's pi times the radius of that little disk squared times the thickness of the disk, which is dx. The radius of this little disk is the height of the strip. So all I need is the height of this strip. What is the height of this strip? Remember, this is the curve, y equals e to the x, and this strip is at x position, just x, a generic x position. So what is this vertical distance? What is the height here? Very good, e to the x. Something that is often helpful in these problems is characterizing a point on the curve, right? The point where that strip touches is x comma e to the x, because we're along the curve y equals e to the x. So now I can come back here, dv is pi times e to the x squared dx, which is pi times e to the 2x dx, right? E to the x all squared is e to the 2x. That's an algebra rule. A to the b all raised to the c is the same as a to the b times c. Now that we have the volume of this little disk, pi e to the 2x dx, I can integrate that to get the volume of the whole solid. I think of this solid as being a bunch of these very thin disks stacked on top of each other. The tool for adding up a bunch of things over a continuous region is an integral. That's precisely what integrals do. And you integrate from the smallest x value in your region to the largest x value in your region. So here my region runs from 0 to 1. So I integrate from 0 to 1. So this is integral 0 to 1 pi times e to the 2x dx. And pi is a constant. It will pop out. I have pi integral 0 to 1 e to the 2x dx. We talked about how to do integrals of this form on Wednesday of last week. This is what we called a micro u sub, right? You'd sub u equals 2x or z equals 2x. Your antiderivative here, I'll continue over here. It's going to be pi, and then antiderivative for e to the 2x is 1/2 e to the 2x. And we evaluate this from 0 to 1. Here being integral e to the ax dx is 1 over a e to the ax plus c from a we call micro substitution. Okay. Now we've done all the hard work. We've even done the integral. All we need to do is evaluate between bounds. I can pop this 1/2 out. We talked about that last time, how constants can pop out of the evaluation bracket. That will make life a little easier. This becomes pi over 2, pi times 1/2. And then I'm just evaluating the e to the 2x piece between 0 and 1. So that's e to the 2 minus e to the 2 times 0, which is e to the 0, which is 1. So this is pi over 2 times e squared minus 1. That is the volume of this solid. All right, here's the whole thing. The magic step is drawing in this strip. Drawing in this strip, rotate just the strip to get the disk, find the volume of the disk, then integrate that. I'm going to lay out the steps next for you just so you have a list of steps. I agree with the comments. Comment came in DM, said, so in general, as long as you know your graphs, you'll be good on this shit. Yep. You got to know your graphs. Got to be able to draw them. Pretty much everything else here is cake. Now, I'll be real with you. Sometimes the geometry can get more complicated than this. And I'll show you examples where that geometry gets a little more complicated. But as long as you know your graphs, you can draw this shit, get in here and label things, think about the geometry clearly, you'll be good. Okay, pausing. Anybody wants a screenshot? Now's the moment. Questions? So the question, why do we not involve pi in the antiderivative step? Pi is a multiplicative constant here. So think a handful of ways I can answer that question. Simplest way is that one of your rules for integrals, if you come back to your integration stuff from the beginning of chapter 5, one of your properties of the definite integral, it's in here somewhere. One of the properties of the definite integral is that constants pop out, right? Integral a to b constant times some function is the same as constant times the integral a to b of that function. So constants pop out of integrals. That's the simplest way to say it. Another way to say it is that even if you left this in here, right, it wouldn't change the antiderivative. The antiderivative of pi times e to the 2x is still pi times 1/2 e to the 2x. If this was pi plus e to the 2x, then the pi would get its own antiderivative stuff. But a constant multiple, just like with derivatives, comes along for the ride. With antiderivatives, comes along for the ride as well. Fair question. Other questions? Anything else we're wondering about this? Okay. So before I give you the general steps, I'm going to show you where the washer part of disk washer comes from, right? We don't just call this the disk method, we call it the disk washer method, and there's a reason for that. Same sort of thing. So there's a second question here. Why did the pi come out when we were working similar triangles? The pi didn't show up in the similar triangle step, but the step right after, we had a pi times what r naught squared over h squared times x squared. That pi popped out for the same reason, that it was a constant multiple. So it's really a property of the integral that constants pop out. So not only the pi popped out there, right? So did the r naught squared and the over h squared. All of those pop out because all of those were constants multiplying my function. Okay. So that example we just saw, the little dv solid we got, the little purple solid, was a disk. The reason for that is that there was no gap between the strip and the axis of rotation. I'd like you to imagine just for a moment, we're going to go back and look at some of those really simple solids. But now I'm going to move the axis of rotation. So here's y, here's x. Here's that line y equals 2 that we had before. And we'll look from 1 to 3 again. Only this time, for my axis of rotation, I'm going to use the line y equals -1. My region is the same region it was before. Still just this region. But when I revolve this region around this axis, I get a more complicated shape now. So if I revolve that region around this axis, the shape I'm going to get this time has this hole punched out of it. All right, again, my art is not perfect, but you get the idea, right? This gap between my region and my axis of rotation induces this hole running through my cylinder. If I were to take a little differential thickness strip and drop it in here, as we did in that last problem, then rather than generating a little disk, this would generate a little washer. So whether you get a disk or a washer depends on whether your region extends all the way to the axis of rotation or not. In other words, whether your strip extends all the way to your axis of rotation or not. So if there is a gap, between the region and the axis of rotation, then the disk becomes a washer, right? You don't get a disk, you get a disk with a hole punched out because the whole solid has a hole punched out. And you can think of this whole big solid here as being a bunch of these disks stacked on top of each other, just like you could with the previous two problems. Here, dV, the volume of this little disk, this disk still has a little thickness, which I'll call dx because it is a little x thickness. But it has two radii. It has one little radius, which I'll still call little r. We'll zoom in here. And it also has a big radius, which I'll call big R. And the way you can find the volume of this little washer is by taking the volume of the big disk and subtracting out the volume of the little disk that's been punched out of it. So that would be pi times big R squared dx minus pi times little r squared dx. And you can factor out the dx on the right and the pi on the left, giving you pi times big R squared, or your outer radius squared, minus little r, or your inner radius squared, times dx. And this is sort of your most general formula for section 6.2. Okay. So let's take a look at a problem where rather than getting a disk, we get a washer and see if we can set this up. We can annotate here, r is the outer radius, which is the, and little r is the inner radius. All right, you ready? Here we go. Let's find the volume of the solid. I'm just going to put dot, dot, dot here. What I mean is find the volume of the solid obtained by rotating the region bounded by the curves, blah, blah, blah. And we'll use for our curves here, y equals x squared, y equals x, and we'll rotate about, again, let's do the x-axis. So first I'm going to sketch these curves. Here's the curve y equals x squared. Here's the curve y equals x. So my region is this stuff. I'm going to rotate this region about the x-axis. And my first step towards finding the volume of the solid you get from this is to draw a little strip in perpendicular to the axis of rotation. There's my little strip. All right, this is the y-axis. This is the x-axis. When I rotate just that strip, I'm not going to get a disc. I'm going to get a little washer. The thickness of that washer is the thickness of my little strip. It's very, very thin, but it's non-zero. All right, here's the little washer I get just from rotating that strip. Thickness is dx, and it has a little inner radius, little r, and a bigger outer radius, big R. We can come back to our 2D picture here and label the little radius and the big radius. Here's the little radius, right? The gap here is what gives the gap here. And here's my big radius. So can we say what little r and big R come out to as functions of x? If this right here is x, right, along the x-axis, what is this distance, this vertical distance from the x-axis up to the curve y equals x squared? What is this distance? Good, x squared, right? It's the y value here minus the y value here. Up here, we're along the curve y equals x squared. So the y value here is x squared. The y value here is 0. Right, so this vertical distance right here is x squared. What is this bigger vertical distance here from the far end of the strip to the axis of rotation, from the curve y equals x? Very good, down to the x-axis. So when I said that thinking about the geometry, right, in addition to knowing your graphs and drawing the graphs, you need to be able to think about the geometry. Here's how I explain this when pressed. This point along the curve y equals x at an arbitrary x value is x comma x. And this point along the curve y equals x squared is x comma x squared. So the y value here minus the y value here is x minus 0. And the y value here minus the y value here is x squared minus 0. Is everybody with me on this? This is the hard part. I want to hear what you're thinking, even if it's like, oh shit. Okay, I'm getting a mixture of responses. So let me write down dv and we'll set up the integral here. So this means that dV, which is the solid of the volume of this little washer, pi times outer radius squared minus inner radius squared dx is going to be pi times the outer radius is x, so r squared is x squared minus the inner radius is x squared, so that squared is x to the 4 dx. Thus, the total volume here is going to be the integral of dV taken from the smallest x value in my region, which is 0, to the largest x value in my region here, which is 1. That's where these two curves meet. I'll set up the integral, and then we're going to go back and talk a little more about the geometry. So this is integral 0 to 1 pi times x squared minus x to the 4th dx. All right, that's not a hard integral. We'll come back to it in a second. Before I evaluate that integral, I'm going to pause. You can write this down or not. What I'm about to do, you can put it in your notes if you want to. You don't have to if you don't want to. But if you got lost in finding these things, you should. So just do it on a separate page in your notes. Little addendum. On graph geometry. If I have here the graph of a function f of x, you'll often see people writing x down there and y equals f of x up here. What that means is that if this is a, then this point on the graph right here is a comma f of a. If this right here is x, then this point on the graph right here is x comma f of x. The reason we write y equals f of x here is because every point along the graph, the y value is f of that x value. When I write x comma f of x for a particular curve, I say I'm characterizing a point on that curve. If I wanted to find the vertical distance from here down to here, I would take the y value here minus the y value here. That vertical distance is just f of x. This is really what we used in that last part. Okay, so the big deal is that every point on a curve, y equals f of x, is something comma f of that thing. For example, if I'm looking along the graph of the natural log function, which looks like this, vertical asymptote here, y equals ln x, and I want to characterize a point on that curve, this would be x comma the natural log of x. And if I wanted to find the distance from here to here, this would just be ln of x. If I were to throw in some other thing here, maybe I call this the line y equals -2. If I wanted to find the distance from this point on the curve all the way down to here, I won't call it r. If I wanted to find the vertical distance from here to here, I would take the y value here, which is ln x, and subtract the y value here, which is -2. So this would be ln of x minus -2, or just ln of x plus 2. You could think of it a few different ways. You could say this distance is ln of x, and this distance is 2. So together you get ln of x plus 2. Or you can just think of it as subtracting y values, right? So to find the vertical distance between 2 points, you take the y value of the larger one minus the y value of the smaller one. That's all. Okay, screenshot it if you want. I'm going to go back to the problem now. 5, 4, 3, 2, here we go. All right, so we're here. This point is along the curve y equals x, so it is of the form x comma x, right? X comma the function, and the function here is just x. So this point is x comma x, which means the distance from that point down to the x-axis is the y value here minus the y value here. And the y value right down here along the x-axis is 0. So that means that this vertical distance is just x. That's what we wrote here. This small vertical distance, right, is the y value here minus the y value here. The curve, the parabola we're looking at there is just f of x equals x squared, y equals x squared. So the y value on that curve is x squared. So you take x squared minus 0. And that's how we got this. All right, I'm going to return to the computation now. This is something you'll want to practice. I can pop out the pi. Constants always pop out of integrals. And I'm just left with the integral from 0 to 1 of x squared minus x to the 4th dx. Continuing that down here, that is pi times, now this antiderivative is just a power rule thing, right? X squared integrates to 1/3 x cubed, minus is this minus. X to the 4 integrates to 1/5 x to the 5. And I evaluate this from 0 to 1. If you plug in the lower bound 0, this and this will both be 0, so we don't get anything. If you plug in the upper bound of 1, both x cubed and x to the 5 are equal to 1. So actually, I think we can fit this here. This is pi times 1/3 minus 1/5. And if you have a common denominator, this is 5/15 minus 3/15. 5 minus 3 is 2, so that's 2 over 15. 2 pi over 15, if you like. Okay, so this is your washer method. What I want to do now for you is lay out the steps, all right? So you have a procedure you can follow. If you get lost or if you run into trouble, just come back to these steps. Step 1, sketch the curves and shade the region. Just like you did in section 6.1, right? Where you're trying to find the area between two curves. Same thing, sketch the curves, shade the region. Step 2, you're going to draw in the axis of rotation. Step 3. You're going to draw in your strip. And you're going to draw it. Does anybody know what this symbol means? This upside down lowercase t, is anybody familiar with that symbol?
Perpendicular?
Yeah, very good. It means perpendicular. You're going to draw in your strip perpendicular to the axis of rotation. Okay, so whatever your axis of rotation is, if that's a horizontal line, you're going to draw your strip vertically. If your axis of rotation is a vertical line, you're going to draw your strip horizontally. Step 4. Rotate just the strip. And draw that little solid. It'll either be a disc or a washer, depending on whether there is or is not a gap. If there is a gap between your strip and the axis of rotation, as we've seen, you'll get a washer. If the strip extends all the way down to the axis of rotation, then you'll get a disc. Step 5, write dv equals pi times big R squared minus little r squared dt, where dt is either dx or dy. So far, everything we've seen is dx. I'll show you a dy problem in a second, depending on whether the strip is vertical or horizontal. Right? So if your strip is vertical, if your strip goes up and down, then its little thickness is going to be a horizontal thickness, and that means your thickness is a dx. If your strip is horizontal, that means its little thickness is a vertical thickness, and hence your differential thickness is a dy. Then your last few steps are to label big R and little r in the picture, in the 2D picture, graph, region, whatever you want to call it, and find big R and little r. And then finally, 7, integrate. You get v as the integral of dv from a to b, where a and b are the smallest and largest x or y value in your region. X values if you're working dx, y values if working dy. All right, these are your steps. That's as granular as I can make it. And this is as close to a formula as anything that exists. Now, if you go hunting around on the internet, you may find more specific formulas. Don't use those, right? You'll get into trouble. As soon as I move the axis of rotation away from the x-axis, the formulas that you'll find online will fail you. And believe me, we will be moving those axes of rotation. Okay. Let me show you a problem where we're working with respect to y. to do a problem where we're rotating about something else. Let's see. Do we have time for both? 12:36 is 11:10 to, what is it, 12? Oh, no, we are over time, aren't we? This class is, let me take a quick peek, sorry. We may have to call it here. 10 to 12:25. Yeah, we've gone a bit over time, so I'm not going to be able to go any further. This is where we're going to have to leave it for today. So next time, I will show you some problems where we work with respect to the variable y, and I'll also start moving that axis of rotation around on you after y values. If working dy. Alrighty, so I am going to go ahead and end the video here, guys. Next time, like I said, we will look at some problems where the axis of rotation is something other than the x-axis. We'll also look at some problems where you're working with respect to the variable y instead of with respect to the variable x. I'm going to open up a new homework set for you. That homework set is going to be due next Monday. Before class on Wednesday, I would like you to work at least 1 or 2 problems from this homework set. That way you'll have kind of gotten some of the juices flowing and you'll be a little bit better headspace to think along with me on Wednesday. If you need the homework from last week extended, please put an extension request in WebAssign. If you need to talk to me about anything, I have an office hour today from 1 to 2. Otherwise, I'll see you guys back here for class on Wednesday. All right, take care, gang.